Okay then, welcome back to the problem solving session of the course Fluid Mechanics and its application, and we are in the week 11 of this course. So in this week session we will be dealing with some of the applications of the all the theories and concepts that we have been reading and learning up till now, and we'll be mainly focusing on the application part of the course. Like, yeah, obviously we have thoroughly seen many examples throughout our courses. Various application based problems we have also solved, and also seen uh, how the basic concepts that we have learned are being applied to various day-to-day life problems. We have seen this application based problem throughout the course, but the today's problem that we are dealing with is basically a is usually regarded or considered to be the highly application based part of the fluid mechanics course. So that's why I mentioned it. And for today's session, we will be dealing with propellers and windmills, and we'll see how the fluid flow analysis across the propellers and windmills are done, and how the what is their basic working principle, and how uh, the efficiency of the propeller and windmills are determined. Then we'll also look into the concept of boundary layer theory, like which is one of the very important part or integral part of fluid mechanics, and how Ludwig Prandtl devised a theory that overcame the D'Alembert's paradox, of which said there was no drag on bluff bodies, so which computed zero drag on bluff bodies or any body in that case, like by the application of potential Euler's equation, which resulted in zero drag on uh, bluff bodies. So, like, usually Euler's equation, as we've seen in the approximate solutions of the universal equation, we saw that for high Reynolds number flow, the viscous terms can be efficiently neglected. But this results in different sets of equation, a singularly perturbed set of equation, which is a reduced order. Basically, it means that initially the Navier-Stokes or the momentum equation was of second order, which had second order derivatives by the virtue of the viscous terms. But as we took the assumption that the Reynolds number is very large, the viscous terms were neglected, which resulted in a singularly perturbed equation, or basically means a reduced order equation, a first order, which resulted in a first order nonlinear equation, and thus resulted in dissatisfaction of one set of boundary condition. That was basically no slip boundary condition at the walls. So only the no penetration boundary condition was satisfied, because of which there was some discrepancy, and which in turn resulted in a paradox, which concluded that there was no drag on the bluff bodies or even streamlined bodies in the case of high Reynolds numbers. So there was a discrepancy, and we will see how the application of Ludwig Prandtl's theory or boundary layer theory resulted in resolving the discrepancy, and how he came up with such a wonderful theory that is still being rigorously used in our modern world, right? So okay, so let's start with it. So for the first part, we will be dealing with propellers. So as you can see, these are usually seen in many scale propeller based aircrafts or small size aircraft. So as you usually know, and here propeller is usually a screw like rotating device that rotates to produce thrust. Okay, thrust basically means the forward force that the plane generates for its movement. Okay, for its movement in the forward direction. And here it basically mentions the basic parts of the propeller, where this part denotes the tip of the propeller, then the edge that faces the incoming air is termed as the leading edge, and the opposite edge where the air leaves the propeller is termed as the trailing edge. Okay, so okay, just wait for 1 minute. Okay, sorry for the delay, just wait for 1 minute. Okay. Okay, then I'm sorry. I apologize for the delay from my side. Okay. Yes. Then the part which is connected, the part of the propeller which is connected to the hub is known as the root of the propeller. Okay. So these terminologies are useful for the in a scenario that for the proper understanding of the working principle of the propellers. But you will see these terms. We'll again use these terminologies while defining the while studying the while studying how the lift and drag forces are generated, how the thrust is generated because of the rotation of these propellers. So these terminologies are important. Okay? That's why I'm describing these terminologies. But as again mentioned, for the sake of saving time, I won't go through deeply to each and every part of the concepts. I will just give a brief overview and go through it. If you have any doubt, you can just go back to the lectures by Professor Gupta. I guess it is wonderfully explained there, and there's no better source. And also, like if you want, then you can also follow any standard fluid mechanics books, so you'll get the required information that you need. Okay then. So now consider a cross section of the propeller. So like as I was mentioning here, if this is a propeller, so consider a particular cross section of the propeller, which would usually, let me just draw it. So consider a particular cross section of the propeller, which would basically be an airfoil. Okay, to basically be an airfoil, and consider that this is at a distance r from the hub. Okay, the radial distance r from the hub. Okay, this is what I'm trying. We are drawing here. So in this diagram, and consider it to be at a certain pitch angle. Okay, so pitch angle would be the angle at which the propellers are oriented with respect to a perpendicular cross section through the middle of the cross section of the propeller. Okay, or the wings, or the blade. Okay, I'm sorry, it would be blade. Okay, or the cross section of the blade. Basically means that if you consider this to be the leading edge, so consider that there is a perpendicular plate going through this cross section of the blade, basically inwards, in direction inwards to this plane of the paper. So that would be that determines a normal a plate in a normal direction with respect to the orientation of the blade. And just consider that this is the angle that the blade makes with respect to this perpendicular plane. Okay, this perpendicular plane, it's an imaginary plane, so this is a perpendicular plane that moves through the middle of the cross section of this blade. Okay, so that is defined as a pitch angle, and this angle is usually can be varied according to the need of the pilot, so that can be varied, and usually in the modern aircrafts it can be varied, but I don't know about the old aircrafts. But for the modern aircrafts, they can be varied because of the need of generating uniform lift throughout the flight. So that's why. Okay, we will see that. Okay, and this is the pitch angle. Okay, and then, like, if we consider that the propeller is moving forward with a certain velocity v, and it is rotating with a certain angular velocity omega, then these two components of velocity v and omega r would result in a resultant velocity denoted by this blue line. Let me just write it as v resultant. Okay, so which would be oriented with respect to the direction, with respect to the with respect to the forward velocity component v at an angle theta. Okay, so this resultant velocity is at an angle theta with respect to the forward velocity v. Okay, just let me, or forward velocity or the rectilinear velocity, whatever you want to say. So I'll just set forward velocity for my terminology. So this is the angle that the resultant velocity makes. Okay, then this angle theta can be determined by this relation, right? Very trivial relation. Omega r by v would be the tan theta of this angle. Okay, and then this theta is greater than the angle of attack by which the wing, or sorry, not wing, the blade approaches the flow. Okay, so you will see that if this is theta is the angle at which the resultant velocity is oriented with respect to the forward velocity component, then this relation gives the value of the angle of attack. Okay, right, and here beta is the pitch angle, and from this diagram also you can clearly see if clearly see that angle alpha represents the angle of attack, which is clearly lesser than the velocity, the angle at which the resultant velocity is oriented. Okay, so I will not continuously say that the angle at which the resultant velocity is oriented with respect to the forward velocity component. I will just say the angle at which the resultant velocity is oriented. Okay, that will make my life much simpler to explain. So I will stick with that explanation. I hope you will be able to understand. Okay, so here you can clearly see alpha would be lesser than the angle of orientation of the resultant velocity, and and here this ratio v by omega is again a very important terminology, is usually known as the advance ratio, or it is the distance at distance that is traveled by the propeller due to one full rotation of the propeller. Okay, so distance, the forward distance, it is the ratio of the forward distance the propeller travels by the virtue of a single rotation of the propeller. Okay, so this is the definition of advance ratio, or you can just tell it's the ratio between the forward velocity component or the rectilinear velocity component with respect to the angular velocity, okay, and the radius of the propeller. Okay, so now we look upon the various components of forces that acts upon the this blade. Okay, so we see that the resultant velocity, I forgot to denote the resultant velocity in all my images. I'm sorry for that. Okay, so the resultant velocity, which is an angle theta, results in a force that acts upon the blade. Okay, and this force can be decomposed into two components, that is the lift and the drag force. Okay, that is the incoming velocity results in a force upon the blade, which is then decomposed into two components, that is basically the lift and the drag component. Okay, lift and drag, and this lift and drag, where the drag is along the direction of the of the resultant velocity, and lift is in direction perpendicular to the direction of the resultant velocity. Okay, so this is very important concept. Like, it's very trivial, but usually it comes in exam. So asks like, which of the following components is perpendicular to the direction of the resultant velocity? Then it's simply the lift, but students usually get confused. So just for the sake of revision or recapitulation, I am trying to mention that. Okay, then here the resultant of the drag and lift is denoted by this sky blue arrow. Okay, this arrow, and this resultant of the lift and drag can then be decomposed into two components again, which is in the forward direction, which is the thrust. You can decompose into two components, where the forward direction, the component of force along the forward direction is termed as the thrust, and the component of force perpendicular to the direction of the movement of the plane or the propeller is termed as the radial component. Okay, and I have represented it as d radial and d thrust because it just denotes a component, or not a component, or a small part of the total force that is being generated by the entire blade. Okay, it's just this force or this component of force is only because of this particular small cross section of the blade. Okay, so this radial component or the d radial force is what that results in the net torque that the propeller has to overcome, so that the plane or the propeller can move in the forward direction. Okay, with a force d thrust. Okay, so see again, this is very simple. Okay, so since if we consider the formula for torque, say T is equal to F cross R. Okay, and F is the force that is perpendicular to the line of application of the force. Okay, so you can clearly see that d radial is perpendicular to the line of application of the force with respect to the propeller, and that's why this force d radial into the radial distance from the hub will give the net torque that the propeller has to overcome, so that the plane can move in the forward direction. Okay, so these components d thrust and d torque are then can be decomposed or represented in terms of the lift and drag forces as the components. So you can clearly see here that the d thrust is represented as the L sin theta minus d cos theta, and the d torque is represented as L cos theta plus L d sin theta into R. Okay, so I hope it was clear, and I hope it was clear. So okay, and one more terminology that let me just tell you here. This distance from the leading edge to the trailing edge, the distance from the leading edge to the trailing edge usually termed as the chord length or the chord of the airfoil. Okay, in this case, chord of the blade. Okay, so this is again an important terminology, so you can tell that, or you can also use to say it as the you can also use this to define angle of attack. You can say that the angle with which the incoming flow approaches the airfoil with respect to the chord is known as the angle of attack of the airfoil. Okay, this again how the useful utility of the terminologies comes into picture. So I guess that's it. Okay, then from here the net power consumed by the propeller or the plane can be given by torque into the angular velocity. Okay, and similarly the net power delivered by the propeller that is being used to overcome that is being used to make the plane move in the forward direction is represented by the thrust into the forward velocity component V. Okay, the velocity at which the plane moves forward. Okay, so this is the velocity or the rectilinear velocity component V. Okay, so implying to both these terminologies, the propeller efficiency can be defined as the net power delivered over divided by the net power consumed. Okay, this terminology, I guess, I hope you remember, because we will use it while the scaling while we do the scaling analysis of the propellers. Okay, or we while we study or analyze the uh, functioning of the propellers in terms of non-dimensional numbers. Okay, or the non-dimensional analysis. So this definition would come into picture while we are studying that. Okay, now this again a very interesting concept, engineering concept, I would say, that is the twist of the propeller blade. Okay, so this is a very subtle thing, like which only an engineer can truly observe. Okay, like whenever you see a propeller, you will see that these propellers are not in a uniform angle. Okay, like the pitch angle of the propeller is not uniform. The pitch angle changes as the radial distance of the propeller. It usually means that as we move, let me just go back to the diagram, it will be much easier. So it basically means that as you can clearly see in this diagram as well, see there is a certain twist in the wing or in the blade of the propeller, where you can clearly see the pitch angle is quite high near this root region, and it's almost it's almost now at a zero angle of attack, or at a zero pitch angle near the tip of the no, I will not say zero, but it's very less. The pitch angle is very less at the tip of the blade. Okay, so there is a certain twist in the blade of the propeller. So it's not uniform. The entire blade is not at a uniform pitch angle. Okay, so why this is needed, I guess we can explain it in the next diagram, and this again is very beautifully explained by Professor Gupta. Nevertheless, I will try to explain it a bit. Okay, so you can focus in this diagram. Okay, so again we refer to the same initial diagram that we started with. Okay, so there might be some overlap in the lines, so I hope you can cope up with it. In the lectures it is very beautifully drawn, but again there is some lack of capability from my side, I guess, that I am not able to draw it very perfectly, but still let's try to understand. Okay, so again, if this dark blue lines, okay, if you are able to see the this dark blue lines denote the components of the forward velocity v and the angular velocity into the radial distance omega r. Okay, this omega r, product of the angular velocity into radial of the radius of the radial distance from the hub. So the components of the forward velocity and the angular velocity are represented by this dark blue line. Okay, so which would again tell us that the resultant velocity is given by this dark blue line. I hope this color distinction will be clearly visible now. So this dark blue line represents the orientation of the resultant velocity, which is at an angle alpha from the chord and the angle theta from the normal from the forward velocity component. Okay, so now if we move inwards or towards the root of the blade, obviously the radius of the blade would go down, right, and consequently the angular velocity would go down, right. So it will result in a reduced value of the angular velocity, right. But again, since the plane is moving with a uniform forward velocity, so the component of forward velocity would remain constant. Okay, so it remains constant. So only the radial component, only the component of the angular velocity reduces, because the radius or the radial distance from the hub has been reduced. Okay, so now here, like if we just move the vectors in the second quadrant, so you can see that this blue line represents the resultant velocity when the let me just write it. Okay, so when the angular velocity was omega r1, and so v r omega r1. Okay, and no, to be clear, I use the same color. So V resultant with respect to the angular velocity omega r1. Okay, and the red one denotes V resultant with omega r2, where r2 is less than r1. Okay, so you can clearly see now that because of the reduction in the magnitude of the angular velocity, because of the reduction in the radial distance from the hub, it resulted in a different value of the net resultant velocity, which is denoted by this, which is again oriented at a different angle with respect to the forward velocity component as well as the chord length. Okay, and you can clearly see here that if this red line denotes the resultant velocity with respect to angular velocity omega r2, it has clearly resulted in a lesser or lower value of angle of attack. Okay, so let me just write it again. So alpha 2 where, or it's alpha 1 where alpha 1 is greater than alpha 2. Okay, so you can clearly see that the B and my sorry for all this inconvenience. Alpha 2. Okay, so you can clearly see here that alpha 1 is greater than alpha 2, and this change in the angle of attack of the blade is a undesirable thing. Okay, this is not usually that the pilots or the engineers want. Okay, what they want is that the angle of attack of the blade should remain uniform throughout the length of the blade, so that a constant value of lift and lift ratio, constant value of the lift to drag ratio, or the CL to CD ratio, is maintained throughout the blade. Okay, so as is mentioned here, for the blade to operate at most efficiently, the lift to drag ratio, or the coefficient lift or to the coefficient of drag ratio, must be fixed. Okay, and there is an optimum angle of attack. AOA basically means the angle of attack, that must be maintained throughout the length of the blade. Okay, in order to achieve a fixed ratio of lift to drag ratio, an optimum value of angle of attack must be maintained throughout the length of the blade. Okay, and that's why, and this is only possible when we twist the blade so that it is a higher pitch angle beta towards the root than at the tip. Okay, so as an engineering need or as an engineering requirement, the pitch angle beta should increase towards the root. Okay, this is a very important conclusion. So let me just again make a box around it. So not only from the course point of view, but as an engineering perspective also, like if you go and visit an airport and see such aircraft, and you are just look, and someone asks like, sir, why there is an twist to the blade angle, like it could also have been uniform, that pitch angle should have been uniform for all the blades, why there is a twist in the blade. So it's a very interesting observation, and I guess now you will have a very good answer to that question, and which is a very interesting thing from my side, at least I believe. So that's why I'm emphasizing it upon this concept so much. Okay, so I hope you also appreciate this concept as well, because it's very subtle but important understanding, and it results only comes when you have a proper understanding of these various components of forces. Okay, so okay, now we look upon the popular performance. Okay, so here basically again we go back to the scaling factor analysis, and we do the scaling factor analysis of the various forces that acts upon the propeller. Okay, so again the inertial force, there is a for us that is along the centrifugal force that acts along the blade, can be decomposed into various scale factors by this relation. So we represent kf omega, basically it represents the scale factor for the centrifugal force that acts on the blade of the propeller, which can be then represented as the scale as a product of the scale factors of uh, density, uh, angular velocity, and uh, the characteristic length of the propeller. Okay, so here kf omega can be represented as would be equal to k rho in k rho into k omega square into kl to the power 4. Okay, so I guess it is quite easily understandable how it is obtained. You can just decompose this relation into its various scale factors. So mass can be scaled into volume times density, with density will result in an L cube factor. So let me just do this one, so others you can do accordingly. Okay, so if f omega, it is mass into omega square L. Okay, omega square L basically the centrifugal acceleration is represented by omega square r. Okay, and that's why or v square by r. So this relation is omega square r basically represents the angular I'm sorry, not angular, or centripetal acceleration. Okay, or centrifugal acceleration. Angular acceleration will be represented by alpha. So that's got it. Now, so if we decompose this relation in terms of their scale factors, so it can be represented again as, say, if you want to decompose it further, so mass can be represented as rho v into omega square L. Then again, if we want to decompose it further, so let me just now to rho omega square L cube. Okay, where let me just simplify it, because rho L cube into omega square L, then clearly see results in rho omega square L cube, which is L to the power 4. Okay, I'm sorry, I was a bit confused. So because L to the power 4, right? Which is, now if we write in terms of scale factors, then kf omega would be k rho k omega square k L to the power 4, which is exactly equal to this relation. Okay, and similarly, the inertial force in a streamwise direction on the towards along the direction of the motion of the plane can be represented as, in terms of scale factor relation, can be represented as kfi would be equal to k rho into kv square into kl square. Okay, then again the viscous forces that acts on the propeller can be represented as kf mu is equal to k mu into kv into kl. Okay, so now to find a similarity rule, first similarity rules, what we do is we divide the inertial component by both of these components by the centrifugal component of the force to get kv by k omega L is equal to 1 and k mu by kv into k rho by k omega square kl cube is equal to 1. Okay, so basically it means that this would be the order of magnitude of this with respect to this and this with respect to this should be 1. So if that holds true, then this relation is satisfied. Okay, this relation is valid. Okay, and now again, if we just represent the these scale factors into the original dimensions to get the pi number, we get that this would be v by omega L, and this would result in mu v by rho omega square L cube. Okay, and these are the pi numbers that we'll usually use to parameterize all our relationships that for the performance analysis of the propeller. Okay, so now we got that the two pi numbers that are that are there in our analysis would be V by omega L and mu V by rho omega square L cube. Okay, and again it can be simplified even further, like if, okay, let's see how it is simplified there. Okay. So if now we give the value, the characteristic value to these parameters or these variables, so we can write that the characteristic velocity component towards the or the rectilinear velocity component can be regarded as the characteristic velocity here. So V is given by V naught. Okay, this is characteristic velocity, and the characteristic length scale L is equal to the diameter of the propeller. Okay, so it's the diameter of the propeller. Like if you consider it to have a certain rotation, it cover a certain circular region, then the diameter of that circular region can be represented as a characteristic length. Okay, or you can even consider it to be the radius of the propeller. Okay, it's completely fine. And finally, so we get that, like if we substitute these values in this relations, we get that the first pi number is the velocity ratio, which is given by V naught by omega d, and second relation simply results in the Reynolds number, okay, which is given by R is equal to rho omega d square by mu. Okay, so again, as I was mentioning, like it is quite simple. Like if you just again consider that in terms of scaling analysis. Okay, I'll just do this one. In terms of scaling analysis, if it is k mu kv, k rho, k omega square and kl cube, then kv can be written as, kv can be written as k omega into kl. Okay, I'm not representing it directly, but I'm trying to represent it in terms of its scaling factors. Okay, so that the cancellation can be justified. Okay, so here now if we cancel out the terms, so this cancels out, this goes down, so it will finally give us k mu by k rho, k omega, kl square. Okay, so again if you check upon the dimensions of this and this, you can clearly see these are exactly the same. Just plug in the characteristic values to these parameters to get the Reynolds number as rho omega d square by mu. Okay, and again if you just compare it even again simplify it even further, so the omega d to d by mu, so this will basically represent the velocity component v. So the dimensionality or the non-dimensional nature of the Reynolds number is preserved. Okay, not to be confused with I am explaining. So again, this velocity ratio in some other books, as mentioned by Professor Gupta, like it's mentioned in the lectures, that is what I wanted to say. It's mentioned in lectures that this velocity ratio is also sometimes termed as advanced ratio, that we saw in the beginning of the session, that which is again defined as a distance moved by the propeller in one revolution of the diameter of the propeller. Okay, to the one revolution to the how basically means that the distance moved by the propeller because of the one revolution of the blade of the propeller. Okay, so now we look upon the various what to say required what not required or the essential parameters that are being that is usually considered for the analysis of the propellers. Okay, or aircrafts. So here we finally saw that the two most important parameters that we are primarily concerned with, like as we go by, we see that we were concerned with these two parameters. Okay, these were the final parameters that we were left with after the analysis, after the force analysis. That was the power consumed and the power delivered. Okay, so this is the first parameter, second parameter, and this is the third parameter. This is propeller efficiency. So these are the three parameters that we will look into it for the analysis of the propeller. So that is what we usually done. Okay, and this analysis will again be done by the help of the scaling analysis. So we'll look into that. Okay, so I apologize again. So I will just request to wait for 2 minutes. I will just come back very soon. So I hope you understand. Just wait for 2 minutes. Okay, then we will resume. Okay. Okay. Again, thanks for waiting, and again, I apologize for delay from my side. I hope you understand. Okay. So as I mentioned that we were interested in these three parameters. Okay. So let me write in different color. So it was first was trust. It's not trust actually. There's power delivered. Then power consumed and a propeller efficiency. Okay. And again, this was again equal to thrust into the forward velocity, thrust into V. This was equal to torque into the angular velocity omega, and this was the propeller efficiency. Okay, basically the ratio of power delivered to power consumed. Okay, so to efficiently analyze these parameters, power delivered and power consumed, and consequently propeller efficiency, we need to understand the variation of these two parameters as well. Okay, so because these two are independent parameters which can be represented by a combination of the primary variables of our problem, that is basically the V, omega, R. So we need to understand how this parameters scale, or just basically do a non-dimensional analysis of these two parameters, that is thrust and torque, and see how these parameters or the non-dimensional form of these parameters vary with respect to our primary variables in our problems. Okay, it is basically the fundamental concept of Buckingham Pi theorem that we usually use, right? We usually used to say that there is certain dependent non-dimensional parameter which is again dependent on some other independent non-dimensional parameters of the problem. Okay, so you can that is what we are trying to achieve. Okay, we will not go through the rigorous analysis of or rigorous steps of the Buckingham Pi theorem to get a proper function relationship, which is we'll exactly get, which is what we'll exactly get, but we'll just go through get a proper understanding. By the proper understanding of the problem, we'll just see how what will be the most suitable functional relationship of this dependent parameter and the respective independent parameters. Okay, so that is what being actually done in the lecture. So I have just followed the same way. So I suggest that you go to the lectures, or if you want to achieve this relationship from your side, that's again well and good. You can follow any standard fluid mechanics book, or again just do the step by step analysis of this problem using the Buckingham Pi theorem, so you get the similar results. Okay, so now again, if we again to take the help of the scaling analysis, so we can decompose the thrust into its, like if we're considering thrust now, so we can decompose the thrust or the scale of the thrust with in terms of the other primitive flow variables in our problem. So the thrust component is basically, again as I told you, it's the inertial component which is along the direction of the movement of the propeller. So it will be the streamwise component of the force, which has the same dimension as this. If you go back to the image, if you go, so you can see it is clearly, it is exactly the same, right? So this is the dimension of the thrust. So again, if we decompose V into k omega into kl, so it can be represented as k rho into k omega square kl to the power 4. Okay, quite simple. Just write kv is equal to k omega into kl. Okay, quite simple. Just write it for reference. Sometimes it may be confusing. So, kv is equal to k omega into kl. Okay, kl. Substitute that, so from that you get this relation. Okay. So now it basically tells us that this T by rho omega square d to the power 4 would be a dependent parameter, which would again depend on various primitive flow parameters, which we saw that from our scale factor analysis, that the two pi numbers upon which the entire problem were dependent were first, that is the that we got was, sorry, the velocity ratio v0 by omega d, and the Reynolds number rho omega d square by mu. Okay, and again it will also depend on the geometry of the problem, which is again basically the geometry of the propeller, where if we consider the radial component, which is radial or the length of the propeller, which is again just considered in this in both of these non-dimensional parameters. So the only parameter that remains in the geometry is the pitch angle. So that is what we need to consider. Okay, so it will also depend on the pitch angle. Okay, so we finally get that. So that's why if T by rho omega d square is the is a dependent non-dimensional parameter, so it will depend on first the velocity ratio or the advance ratio, second the Reynolds number, and third the geometry, which is basically the pitch angle. So there is a very interesting observation that was seen that for higher Reynolds number, like when I'm just mentioning as infinity, but basically means that for very high Reynolds number, this dependence of the thrust coefficient, basically this ratio, if we term it as a thrust coefficient, so and represent it as Ct. Okay, so it is observed that for higher Reynolds number, the dependence on thrust coefficient on the Reynolds number is quite negligible. Okay, I'm not saying it's zero or it's completely independent, but basically tells us that for high Reynolds number, the dependence of the thrust coefficient is almost negligible on Reynolds number. Okay, the dependence of the thrust coefficient on Reynolds number is almost negligible when the Reynolds number is very high. Okay, and usually for the application or for the application of these blades, like this is basically like for the usual application, that is basically for aircrafts, the Reynolds number on these blades are usually very high. Okay, and that's why this assumption or this approximation is very accurate. Okay, it's very accurate because there is no application or any engineering use to this problem if the Reynolds of the aircraft is not moving with some threshold velocity. Okay, beyond which beyond that lesser than, if the value of velocity is lesser than the threshold velocity, the aircraft cannot take off, right? So there will always be a threshold velocity that the flight needs to overcome to take off, right? And that threshold velocity itself would be in the turbulent flow regime. or in a very high Reynolds flow regime, right? And that itself tells us that since the Reynolds number itself is very high, even for a threshold velocity, so it will basically mean that for the flight while it is in its functioning condition, or while it is moving or traveling, it will certainly be at a velocity higher than that threshold velocity. So Reynolds number with respect to that velocity will be very high. So we can easily or efficiently consider this, simplify this dependence on Reynolds number, or just disregard this dependence on Reynolds number of the thrust coefficient. Okay. So if we consider that, it was observed that the thrust coefficient varies according to this plot, where you can see that x-axis denotes the advance ratio. It is basically V by omega d, and the y-axis denotes the thrust coefficient, and these are the various angle of pitch angles that is being presented here. Okay, and you clearly see that for higher advance ratios, we need we get higher thrust coefficient, but also we need higher pitch angles. Okay, or it's termed as blade angle here, so it's just that. Okay. Similarly for torque, now, like, since we consider one of the parameters, so the other parameter that is being left here is the torque. Okay, so similarly we can decompose the torque into its scale factors to get the scaling of the torque. So we can see that the scale factor for torque, the scaling factor for torque is it can be given by k rho into k omega square into k to the power 5. Okay, which will tell us that q by rho omega square d to the power 5 is a dependent parameter, which will again be dependent on the same independent parameters, that is basically the advance ratio, Reynolds number, and the geometry. Okay, so now once we have the functional relationship or the non-dimensional parameterized form of the torque and thrust, now we can deal with the two important parameters that we were initially discussing, right? It is basically the power propeller efficiency and the this is basically the power delivered and the power consumed, and consequently the propeller efficiency. Okay, so I will just skip fast. I'll just skip a bit fast, because now you know how everything is done, so we can just move a bit fast. Okay, so the power supplied is measured by by the product of the torque to the angular velocity, whose the scale factor of the power delivered would be given by this relation. So Cp, if it represents the power coefficient, so Cp would be equal to P in divided by rho omega cube d to the power 5. Okay, which would be again a functional dependence on the advance ratio, Reynolds number, and the flow geometry. Okay. Similarly, for the power delivered or the output power, the scale factor form is represented by k rho into k omega square k to the power 4 into kV. Okay, so again it will give us that the power coefficient would be P out by rho omega square d to the power 4 V naught. Okay, which will again be a functional, which again have a functional dependence on the advance ratio, Reynolds number, and the flow geometry. Yeah, flow geometry. Okay, which is basically the pitch angle in this case. So since we now have both the power coefficient for the power output and the power input here, so now we can efficiently define the power efficiency, right? So now we get that the power efficiency eta could be defined as P out by P in. Okay, so which will again be equal to TV naught divided by Q omega, where Q represents the torque. Okay, so if we again deduce these relationships into their if we represent this in terms of the primitive variables now, so we get that we get two equations. Okay, first is that this would be equal to Ct by Cq into the advance ratio, or also it will be equal to Ct by Cq into J. Okay, I'm sorry, I just interchanged it a bit. So if we if we efficiently cancel out the parts various variables from this equation, we get the final equation as Ct by Cq into the velocity ratio, or also it will be equal to Ct by Cq 1 by 2 pi into Ct by Cq into the advance ratio J. Okay, where it was J was represented as, use this color, J was equal to V naught by eta, sorry, not eta, nd. Okay, and Ve was V naught by omega d, and omega is equal to 2 pi n. So this 2 pi is what that comes into this relation. Okay, now so this plot is again a very interesting plot, so I wanted to explain it a bit. So this plot is very interesting in the fact that you can clearly see that if, like, the y-axis represents the efficiency of the propeller and x-axis denotes the advance ratio, you can clearly see that for almost all values of advance ratio, the propeller efficiency almost remains constant. Okay, see, it's almost constant. Okay. But the interesting thing to observe here is that as the advance ratio increases, in order to maintain the same efficiency, the pitch angle or beta should also be increased. Okay. So what does it mean? See, the velocity ratio V is given, or the advance ratio, say, let me write it in terms of advance ratio. J is represented by V naught by eta d, n into d. Okay, so now here for so now it basically means that now if this ratio increases, like if V naught increases, or the velocity with which the plane is moving, if it forward increases, so J will go up. Okay, it will obviously go up, right? So now if J goes up, if the if the advance ratio goes up, then in order to maintain the same efficiency, we need a higher pitch angle. Okay, it basically means that in order to because this V naught is a variable parameter, right? It changes according to the need of the flight, according to the need of the pilot. Okay, so if he wants to move faster, or if he wants to move into a certain destination in a shorter time, he needs to move fast. Okay, and also it also changes with the incoming speed of the wind as well. Okay, so this is a variable parameter. This changes. Okay, this changes as per the need of the pilot. Okay, so now, but if this changes, if this parameter changes, then it means that in order to have the same efficiency, or you have to have the highest efficiency or maximum efficiency, the parameter beta should also be under the control of the pilot. Okay, that is what I was telling from the beginning. Like while we were discussing the geometry of the propeller, we told that beta should also be a variable, so that it can be varied by the pilot as per their needs, so that the efficiency could be maintained, or maximum efficiency could be maintained. Okay, so that's why you can clearly see that now, in order to have a maximum efficiency, this beta angle beta should also be a variable or a controllable parameter by the pilot himself. Okay, so that the maximum efficiency can be maintained. Okay, so that's what I want to discuss here. So I guess that would be all from for the popular part. So now again I will just move move now, since you know all the basic terminologies, so I will just move a bit fast for the windmills also. Okay, so windmill, I guess you are quite familiar with. It's one of the very important tools or in order that is being used by engineers to harness wind energy. Okay, and one of the most common types of wind turbines are the horizontal axis wind turbine, okay, which are also abbreviated as HAWT or HOT. Okay, so now I won't go on to describe each and every term in this diagram. I hope it was quite beautifully explained by Professor Gupta in his lectures. So I hope that's fine. So if I talk, so these are the blades of the wind turbine, where distance from the tip to the root will be the radius of the blade, and the incoming wind comes at a certain velocity which rotates the wind turbine, and this rotational energy is then converted into an electrical energy by the help of an electrical generator, which then generates electricity, which is again then used to or stored stored and then supplied to the households. Okay, so that is basically the working principle of wind turbines. So again, so in order to analyze the wind turbines, now we will take a bit different approach. Now we take a control volume approach that we studied while we are studying the integral form of the governing equations, basically RTT, control volume, control surface, integral form, differential form. I hope you recall now. So control volume analysis. Okay, Lagrangian approach, Euler approach. So when we are dealing with those concepts, we will we'll use those similar concepts here again as well. Okay, for studying the power gen the working principle of wind turbine. Okay, so if we consider this dotted box as our control volume, okay, and this line represents a stream tube. Okay, basically a bundle of streamlines. Okay, so one approximation that we take is that beyond this stream tube, the disturbance in the flow field is considerably very small, considerably very less. Okay, considerably small. So all the interesting phenomena or flow physics that is taking place is within the confinements of this stream tube. Okay, this is one of the approximation. It is quite accurate. Okay, it's not that vague or just made by ourselves. No, it's a very good approximation that the researchers have usually take for the analysis of the wind turbine. Okay, or the windmill in this case. Basically the same thing. And so here, if we consider this to be our control volume, this dotted line to be our control volume, and this solid lines to be our stream tube. So if we consider that so if we now consider this to be our stream tube, so one of the approximations or not approximation, one of the very definition of streamlines was that there is no flow across a streamline, right? This was one of the very important conclusion that we got while studying the streamlines and stream tubes, right? There can no flow outside the no flow across the streamlines. Okay, so if this stream tube represents a bundle of infinite number of streamlines, then it usually then it is usually representing that there is no flow across this stream tube. Okay, so we can do all our analysis within this stream tube now. So now if we consider that V1 is the velocity at which the incoming wind is approaching, that is basically in this diagram, that if the wind is approaching with a velocity V1 and leaving the turbine with velocity V2. Okay, this is what being represented here. Okay, so the area of at the inlet would be the inlet area of the stream tube. Okay, so A1 would basically be the area of inlet of the stream tube. Similarly, now V2 represents the velocity of the air after the wind has or air has interacted with the wind turbine. Okay, so V2 is the velocity at the exit, and A2 represents the area of the exit of the steam tube. Okay, so I guess the areas are now quite clear. What are the areas? And here you can clearly see that since the flow has the wind turbine has extracted energy from the wind, right? Because the wind is coming with certain kinetic energy, that is what being extracted by the wind turbine, or basically used by the wind turbine to rotate, and this rotation energy is then again converted into electrical energy, right? So basically means that the energy is being extracted from the incoming wind. So it basically means that since it is essentially kinetic energy, or the majority of the energy, incoming energy, is in the form of kinetic energy, so basically means that since the energy is being reduced because some part of the energy is being extracted by the wind turbine, so the reduced energy would imply that the velocity of the flow has been reduced. Okay, why? Because I'm telling this because the majority of the energy, that incoming energy, is in the form of kinetic energy. Okay, or you can also consider it to be entirely kinetic energy, because that is the approximation that is being usually used for our analysis, right? We assume that the entire incoming energy is in the form of kinetic energy. Okay, so if a portion of this kinetic energy is now being extracted by the wind turbine in order to generate some electrical work, then it will consequently result in a reduced velocity at the exit, right? Like, since the kinetic energy is being reduced now, so the velocity of the wind after crossing the wind turbines would consequently reduce, right? That is what been done here. So if V1 is not greater than V2, in order to maintain mass conservation, why? Because there is no flow of fluid across the stream tube, so the mass that comes in has to go out. So in order to conserve mass, or in order to satisfy mass conservation, we need to have A2 to be greater than A1. Okay, and that's what this diagram represents. Okay, so now I guess we will be short of time, so I guess I will now go a bit fast, and sorry for the inconvenience from my side. I request that if there's any doubt, you just go back to the lectures to have proper clarification. Okay, so I'll move a bit fast because we have to again discuss boundary layer theory and lots of problems. So okay, so applying momentum conservation, I guess I can just skip through this derivation. Okay, you can refer it in the lectures. So the momentum conservation will give us this relationship. So from this from the momentum conservation and energy equation, we get that the velocity at the windmill disc, or the velocity at the wind turbine, is equal to half of V1 plus V2, where V1 is the velocity far upstream from the wind turbine, and V2 is the velocity far downstream from the wind turbine. Okay, it is the average of these two velocities. Okay, now the power extracted is again represented in terms of these two velocities. This is basically the velocity of the incoming flow and the velocity far downstream to the wind turbine. So from that relation we get that using that relation we get a function the power extracted to be of this form. Okay, so the function relationship we get for the power extracted is of this form, where you can see that which is then given by rho a V1 cube by 4 into 1 plus b and 1 minus b square, where b is equal to v square by v is equal to v2 by v1. Okay, so now you can now you can clearly see that if b increases, it results in increase of this parameter and a reduction in this parameter. So you can clearly see that this would result in a maximum at some point of the in the domain, okay, at some point in the domain. So if now b varies from 0 to 1, you can see that the maximum value of power is obtained for b equal to 0.5926. Okay, so here if we represent if we define the power coefficient as the net power extracted from the power from with over the ratio of the net power extracted and the net power input, so we get that Cp would be equal to half 1 plus b into 1 minus b square. Okay, so 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 in order to find the maximum value of Cp, you can just clearly it's again a very simple trivial calculation. You need to find dCp by this derivative equal to 0. So you will find that to satisfy the relationship, we get b is equal to 0.33, and the value of Cp for b equal to 0.33 is equal to 0.5926, which is the maximum value of the power coefficient that can be extracted from a wind turbine. And this is again termed as the Betz limit. Okay, it's a very popular terminology which is being used in the entirety of the engineering community. So this value is very important to remember. Okay, Betz limit, so whose value is 0.5926. okay, so I hope that you remember this value because you will be using it in one of the problems. So I hope you remember this. Okay, so now we look into boundary layer flow. So I guess I have extensively discussed boundary layer flow in at least in my session, like time and time again, like while we were discussing scaling analysis. I even did the boundary analysis as one of our problems, and even derived the boundary layer equations for flow wave flat plate. Okay, so again, I guess why I'm explaining this, because I'll be doing exactly the same thing in this remaining part of the session. So if I'm a bit fast or just move fast, just skip some of the concepts, you can again just go back to the previous videos so that you can get the reference. Okay, it is very beautifully explained in the previous session, but still I will try my best to explain the most of it in the best way possible. So I hope you cope up with me. Okay, so okay then. So for the boundary layer flows, we non-dimensionalize the governing the flow parameters with respect to the characteristic scale. So I will just move fast a bit, and then we find that this is the form of the non-dimensionalized equation. Okay, so and these are the respective boundary conditions. Okay, so once if we represent these non-dimensional numbers in terms of if we represent these non-dimensional parameters in terms of the popular non-dimensional numbers, we find that the ancillary term, the non-dimensional parameter with respect to the ancillary term is actually the Struhan number. Then the non-dimensional parameter with respect to the piezometric pressure gradient term is the Euler's number, is the inverse of the Euler's number, and the non-dimensional parameter with respect to the viscous term is the inverse of the Reynolds number. Okay, it's a very popular and simple it's a very popular equation. So I hope you are aware with the non-dimensional terms that comes in the picture. Okay, again now for high Reynolds number flow past the immersed bodies. So I hope just okay. So for high Reynolds number flows past immersed bodies, so these types of flows are governed usually in these types of flow the viscous forces are neglected. You will eventually see why. And these types of flows are then governed by the Euler's equation. Okay, we also saw Euler's equation, if you remember, recollect, we saw the Euler's equation in the while we were discussing the in-viscid flow theory. Okay, or the potential flow theory. We'll also discuss. Let me just write it. Okay, just for so this is the interesting part, right? We told while we were discussing the potential flow theory, we told that we are Euler's equations come into picture. Why? Because the viscosity of the fluid is neglected. Okay, that was a very crude approximation, or very crude approximation that we put right before we started solving the equations. Right, we told right before itself, right upfront itself, that the flow is inviscid. There is no viscosity, and that's why we can just directly disregard the viscous term. Okay, there was no concept of Reynolds number that came into picture while discussing the inviscid flow theory. Okay, there was Stokes number and Euler's number that were usually considered. Right, so Reynolds number didn't come into picture. So there also the Euler's equation are varied. Why? Because we are discussing an inviscid flow theory. Okay, but now in the case of high Reynolds number flow, the viscous terms are neglected. Why? It's because the Reynolds numbers are very high. See, this term is basically the inverse of the Reynolds number, right? And as Re approaches infinity, this term will go to 0, right? And that's why this term can be efficiently neglected for higher Reynolds number flow. Then again the governing equation would result in the Euler's equation. Okay, so we see that that is what we observed here. So Euler's equation again comes into picture while discussing higher Reynolds number flow. So here also, since the equation has become singularly perturbed, or the order of equation has been reduced, so no slip boundary condition cannot be satisfied. Okay, and potential flow and the flow around the body can be considered to be potential flow. Okay, and this relation results in a zero drag on the body. Okay, this is the structure of, or the basic principle that is being used for analysis of high Reynolds number flow past immersed bodies. Okay, now if we consider this application on aerodynamics, okay, or while studying flow above streamlined bodies. Okay, I will not say directly aerodynamics, I will also mention streamlined bodies. So here, if we apply these principles, these principles again correctly predict the lift coefficient, which is given by this relation, which is again of order 1, which is again correct, and it matches quite well with the experimental results. Okay, that's the interesting part. It predicts the drag coefficient to be 0. Okay, but again the experimental results show that the drag coefficient varies as 1 by square root of the Reynolds number. And if Reynolds number goes to infinity, it will again tell us that the drag would approach 0. And thus, these results are quite acceptable in the case of streamlined bodies. Okay, but while dealing with block bodies, this is basically bodies that are not streamlined, okay, and have certain considerable amount of form drag or pressure drag, there again it predicts the drag coefficient to be 0. Okay, because no viscous forces are considered, or so the equation, since no slip boundary condition is not satisfied or not considered, it will consequently or surely result in no drag forces on the body, right? So that's why the drag coefficient is found to be 0 in the case of block bodies. But the experimental results now show that the drag coefficient is actually of order 1. That is the discrepancy that being found here, and this discrepancy is in turn termed as the D'Alembert's paradox. Now, to deal with D'Alembert's paradox, Ludwig Prandtl in 1903 put forward the idea that high velocities or high Reynolds number flows, that at high velocities or high Reynolds number flows, the no slip boundary condition causes a strong variation of flow speeds over a thin layer near the wall of the body. Okay, he basically told that there would be a variation in the flow velocity, then that the no slip boundary condition would be satisfied, and the variation of the velocity from 0 to the free stream velocity would be there, but it will occur in a very small thin strip of the flow, which will almost stick to the wall of the body, which he termed as the boundary layer. Okay, the power of Prandtl's formulation was its ability to explain the large drag coefficient observed on block bodies. Okay, and now after the boundary layer theory was devised and applied on block bodies, then he found that, then then it was observed that the drag coefficients were of order 1. Okay, so the D'Alembert's paradox was solved or taken care of by the boundary layer theory of Ludwig Prandtl. Okay, the rapid change of flow speeds near the wall leads to a generation of vorticity there and to the viscous dissipation of kinetic energy in the boundary layer. Okay, and the energy dissipation which is lacking in the inviscid theories results in flow separation in block bodies. Okay, so I guess it's quite self-explanatory. So it basically tells us that this viscous dissipation of kinetic energy in the boundary layer, this viscous dissipation phenomenon was not observed in the inviscid theories. So that's why that is what had resulted in the discrepancy of the Euler's equation or the application of Euler's equation over block bodies, which had resulted in discrepancies in the discrepancies in the value of the drag coefficients. Okay, so now what we do is in order to tackle D'Alembert's paradox, Ludwig Prandtl came up with different scaling across different coordinate directions. Okay, so instead of scaling the y coordinate or the normal or the coordinate in the normal direction with respect to the boundary with respect to the surface of the body, there he scaled this normal component of the I will just say normal coordinate as scaled it as the thickness of the boundary layer. Okay, delta c. So after he has done this scaling, all the discrepancies that were there in the Euler's equation or the potential or for applying potential for theory over the block bodies were taken care of. Okay, so we will see that. So now if we apply this scaling in the continuity equation, we see that u naught L should scale as v naught by delta c. So which will give as v naught, which will give that v naught should scale as u naught delta c by L. Okay, and again, now if we consider the x momentum equation, it is basically given by this equation. So we take we do the scale we do the non-dimensional analysis of each and every term in the governing equation, which then gives us which then finally gives us this form of the equation. I'm just skipping past some of the steps so that we can save time and discuss problems. So here we get that since this term represents the inverse of the Reynolds number, so here since Reynolds numbers are very high in the case of boundary layer flows, so since Reynolds numbers are very high, this term would go to 0. Okay, this term would go to 0, and we will only be left with these two terms. Okay, this one and this one. And see here, this is not cancelled out. Why? Because delta c is the scaling of delta c is much less compared to the characteristic length scale or the length of the flat plate. Sorry, not length of the flat plate, or the characteristic length scale of the body, because right now we have not imposing that this flow is over a flat plate. Okay, this flow can be over any surface. Okay, so delta c is usually very less than the characteristic length scale. So that's why this term cannot be cancelled out. And again, since this term has to be of the ratio of should be of order 1, because these two terms in the right hand side are of order 1, so this again results in a very important conclusion that tells us that the boundary layer thickness scales as the square root of the inverse of the square root of Reynolds number. Okay, so this is a very important conclusion again that we get from this analysis. And since all the terms in the governing equation of order 1, and there must be a pressure there is a pressure gradient along the x direction, so again, I'm sorry, I need to explain this, like why there is a pressure gradient. See, we see that for this boundary layer flows, u is actually a function of x. Okay, and u increases as the flow moves forward. Okay, and since u is increasing because of the since there is an increase in the velocity of in the forward direction, there must exist a pressure gradient along this direction so that the increase in the velocity can be justified. Okay, and that's why this term must be there. And since these terms are of order 1, all are of order 1, then it basically tells us that this term should also be of order 1. So it basically it will basically tells us that the piezometric pressure difference would scale as the kinetic energy. Okay, obviously why I will just again reiterate, as I told it, pressure behaves as the scales as the one that dominates the flow or drives the flow. In this case, the flow is being driven by the inertia of the flow, and that's why pressure would scale as the kinetic energy of the flow. Okay, it's quite simple. So from the x momentum equation, the boundary the non-dimensional form of the boundary equation that we're left with is of this form, where the derivative with respect to the x coordinate has been dropped off, and so we are left with this equation. And these two are the important conclusions that we get from the non-dimensional analysis of the x momentum equation. Okay. Similarly, from the y momentum equation, if we do the same non-dimensional analysis, we get that the important conclusion that we get that the only dominating term that is there in the y momentum equation is the pressure gradient term along the y direction, which tells us that the pressure gradient along the y direction is equal to 0. Okay, this is an important conclusion that we get from the non-dimensional analysis of the y momentum equation in the boundary layer. Okay, so finally, if we convert this governing equation into the dimensional forms, we get the boundary layer equations. Okay, where we get the continuity equation remains the same, and the x momentum equation, there are two modifications. First is that the second order derivative with respect to the x coordinate has been dropped off, and secondly, the pressure gradient now is only a function of x. Okay, it only depends on x because dou p by dou y is equal to 0, so it's only a function of x. Okay, so this becomes a complete derivative, so which are then subjected to two boundary conditions. That is basically u at y equal to 0 is 0, and u at y tends to infinity is u of x, basically a free stream velocity with which the flow is approaching the surface. Okay, not reflected, the surface. Okay, now the pressure determined at the wall from the inviscid flow is impressed on the boundary layer. Why? Because there is no variation of pressure across the boundary layer, okay, or towards the normal direction. So the pressure at the wall, dou p by dou x at the wall would be equal to rho dou u by dou x, which is again being obtained from by applying the boundaries equation at this by the application of boundaries equation. Okay, it's again quite simple. It was done in the previous session, so you can just follow that. Okay, so the final form of the boundary equation now can be written in this form: the rho dou u by dou x plus v dou u by dou y equal to rho u dou u by dou x, where u is the capital U, not the small u. Okay, it's the capital U. Okay, I hope it's clear. It's some known function. Okay, it's not unknown. Unknowns are the u and v, but here capital U is known. It's some known function that that we known before we start to solve the equation. Okay, so this is a known parameter. Plus, so this is the final form of the boundary equation. So what have we achieved after? So now we look into what have we achieved after the application of boundary equation. Okay, so thing is that one of the equation has been dropped. Okay, so the y momentum equation is disregarded. Why? Because the implication of dou p by dou y is equal to 0, because the conclusion that we get, that is dou p by dou y equal to 0, has its implication on the x momentum equation that is being observed in this term, right? So it is considered in this term itself. So one equation is dropped, y momentum equation is not considered. Second, the three dependent variables are now reduced into two dependent variables. Initially we started with u, v and pressure term, but since we found that pressure does not vary along the y direction, and this relation holds true for flow within a boundary layer, so the pressure term is being dropped off, so we are only left with two dependent variables, that is u and v. And finally the dou square u by dou x square term is being dropped off. So again, so these are three simplifications that we get after the application of the boundary layer assumptions. Okay, now if we consider flow over a flat plate, the interesting result is that now, since this equation, if we go look back in this equation, since u for a flow over a flat plate, u is not a function of x, u is a constant velocity, so u is equal to u infinity throughout the flow over the flat plate. So since this term was approximated as this in the boundary equation, so this term can efficiently be cancelled out from the equation because u naught is constant. Okay. So we are only left with this equation which satisfies the boundary condition that u and v equal to 0 at y equal to 0 and u tends to infinity as y tends to infinity. Okay, so we are left with these boundary conditions, and this boundary equation is a parabolic equation because only the highest order derivative is the y term, and if you just check the determinant of the discriminant of the this form of the equation, au xx plus bu xy plus cu yy, so we'll find that this governing equation is actually a parabolic equation and can be solved using some using marching schemes. Okay, so this equation can be solved by using a starting solution at x equals 0 and then marching along x. Okay, so this equation especially would result in marching solutions. Okay, so in order to solve this equation, this was again solved by Blasius, who was Prandtl's student, and which resulted in a very popular set of solutions known as the Blasius solutions. So he used the concept of self-similarity, or basically the self-similarity of in the velocity profile, which basically tells us that the form of the velocity profile would remain same throughout the flow over the flat plate. Okay, so even if the velocity increases, the magnitude of velocity increases as we move across the flat plate, as we move along the flat plate, the form of the velocity profile would remain same. Okay, and that's why this equation can be used by the help of self-similar solutions. Okay, or self-similarity, from which the final governing equation was given by this form, which is again a third order nonlinear ODE subjected to these boundary conditions. Okay, and once this equation was solved, it is solved like usually at present, like this equation can be easily solved by using some numerical methods. One of the very popular ones is the ODE 45 at MATLAB. So we just use that MATLAB module and solve this equation. So we can, from that you will clearly see that for f dash equal to 0.99, eta would be equal to 4.91, and I have not drawn the profile, but you can see the profile in the video lecture. So that will correspond to the value of the velocity, where u will be equal to 0.99 of the u infinity. That's basically the boundary thickness. So it gives that delta is equal and after reducing eta in terms of x and delta, we finally find that delta is equal to 4.9, or in a much simpler manner, delta by x is equal to 4.91 times x into REX. Okay, and this is one of the very and this is also known as the Blasius solution for flow over flat plate. And also sometimes this factor 4.91 is also sometimes also used as 5. Okay, so instead of 4.91, many people or many authors in itself use it as 5. Okay, so any of the two can be considered to be correct. Okay, so don't get worried if your forgot this parameter. Okay? You can remember 5 as well. So both are equally correct. Okay, and this relation is only valid for laminar boundary layer. So for valid up to a Reynolds number of 4 into 10 to the power 5, or in some books it's also represented as 5 into 10 to the power 5. Okay, so okay, again after using the same relationships or same results, the shear stress was found to vary as 0.332 into rho u infinity square by square root of Rex, and the skin friction coefficient was found to vary as 0.664 into square root of the local Reynolds number. Okay, Rex basically represents the Reynolds number at a particular x coordinate over the flat plate. Okay, so these are like very simple results or simple equations that have very huge area of applications. So it's wise, it will be very wise if you could just remember this relationship, that delta is equal to 5 times x by square root of Rex, or skin friction coefficient is equal to 0.664 divided by the square root of local Reynolds number. So it will be very wise if you remember these relations. Okay, or especially these constant values. Okay, then the drag coefficient over the flat plate was found to be 1.328 divided by square root of the Reynolds number at the trailing edge of the flat plate. Okay, I'm moving a bit fast so that I can cover some problems, so that that will be more helpful for you. Okay, so these are the conclusions that we get from the Blas's solution. Okay, so now again okay, so you can just briefly go to the question for a while, then we'll see how we can approach this question. Okay, quite straightforward. This question was again being dealt in the lectures of Professor Gupta. So yes, so in order to save time, I guess I can skip these two questions right now for a time being. So I'll skip these two questions that were discussed by Professor Gupta and directly go to some more questions. Okay, that will be more beneficial for us. Okay, so now look in this question. Water flows over a flat plate at a free stream velocity of 0.15 meter per second. There is no pressure gradient and the laminar boundary layer is 6 mm thick. Assume a sinusoidal velocity profile is given by this. For the flow conditions stated above, calculate the local wall shear stress and the skin friction coefficient. Okay, basically you need to determine tau wall and CF. Okay, and these are the value of the dynamic viscosity and the density of the fluid. It is basically water. Okay, so from here we can find that tau is equal to mu dou u by dou y, and then again sorry, since it only depends on y, it can be written as okay. So if we take the derivative, we find that this is equal to mu u infinity by delta into pi by 2 cos pi by 2 y into y by delta. Okay, just now substitute since we know all the values now, just substitute. Oh no, sorry. So okay, you can just simplify the equation a bit further. Substitute the value of pi by 2 in this, at least value of pi by 2 in this expression. So you get that tau is equal to 1.57 mu into infinity by delta into cos pi by 2 y by delta. Okay, so now at the wall y equal to 0, so substitute y equal to 0 in this expression to get that the wall shear stress is equal to 0.04 Newton per meter square. Okay, and again, since we also need to find the skin friction coefficient, it will basically be the ratio of the wall shear stress upon the kinetic energy per unit volume. So once we do that, we find that CF would be equal to 3.5 into 10 to the power minus 3. Okay. Now consider this equation. Okay, this again a very simple equation. Simple question where all the parameters or values and the relations are given. You just need to substitute the values to get the result. Okay. A pump has a diameter D is equal to 53 centimeter, and N, or the number of rotations that it takes, is 1500 rpm. Okay. Estimate A, the discharge, B, the head, C, the pressure rise, and D, the brake horsepower for this pump for water at 15 degrees Celsius at best efficiency. Okay, I guess it is at best efficiency. I did wrong. Okay, it's not N, it's actually at best efficiency. Okay. So it is given that at best efficiency for the working of this pump, the coefficient of or the capacity coefficient is given as CQ. Or before that, let's just go to these different coefficients. Okay, so for this pump, the capacity coefficient is represented as the ratio of the volume flow rate divided by the number of rotations times the cube of the diameter. Okay, the head coefficient CH is defined as GH by N square into D square, and the power coefficient CP is equal to the ratio of the brake horsepower divided by the ratio of the density into N cube into the fifth power of the diameter. Okay, so once you know this coefficient, so it is told that at best efficiency, the values of these coefficients are given as CQ is equal to 0.0015, CH is equal to 5.0, and CP star is equal to 0.65. Okay, star represents the value of this coefficient at maximum efficiency. Okay, so now I guess this question is very trivial. Now you have the value of these coefficients at maximum efficiency. You know the value of this most of the parameters here. You just need to find the value of the parameter that is being asked here. Okay. First, the discharge, so just substitute the value of N and D cube in this equation and multiply with CQ star to get the value of Q. Okay, so basically we do that. So here D is equal to 0.53 meter, N is equal to 55 rounds per second now, RPM to rounds per second. So at 15 degrees Celsius, the density of water is 998 kg per meter cube. You can take it 1000 also, no issues. Then from the above mentioned values, at the best efficiency point, or BEP, as it is termed, as it is usually termed as. So Q star, or the mass volume flow rate at the best efficiency point is equal to 0.195 into 25 into 0.53 cube. Okay, which will give us the volume flow rate as 0.428 meter cube per second. Okay. Then the head at the best efficiency point can be found from this equation. Okay, just it will be CH into N square D square divided by G. Okay, so we find that. So substitute the value of CH star in this equation, which was 5 in the question. Yes, it is 5. So substitute this value here, and substitute the value of N, which is 25 as we found out, and the diameter of the pump, that is 0.53 meter, and divided by the acceleration due to gravity. So we get that H star is equal to 89.5 meter. Then also for C, we are asked to find a pressure rise at the best efficiency point, which can again be given by this relation, del P is equal to rho G H star. So just substitute since we know H star, so just substitute the value of rho and G to get that the pressure rise at BEP, or the best efficiency point, is 876 kilopascal. And finally, we were asked to find the best power at the best efficiency point. So P star can again use this equation to find this brake horsepower. So we get P star will be equal to CP star into rho N cube dt power 5. Okay, so just substitute the value of rho N and D here to get that P star is equal to 570 horsepower. Okay, divide this by 746 watt to get that P star is equal to 570 horsepower, because it's again it's very standard in unit of power that is used for industrial purposes. So we represent it as horsepower here. Okay, now consider this equation. Okay, these are again very simple questions, but you need to remember the formulas. Okay, that is what we are trying to achieve here. Okay, so the wind is blowing at 10 meter per second. With how much power is the wind hitting the turbine if the blades are 45 meter long, assuming that the wind turbine is at the sea level? Okay, the formula is very simple, but you need to know what are the things that we need to substitute. Okay, so here it is told that the velocity of the incoming wind is 10 meter per second. Okay, so we are asked to find the power with which the wind is hitting the wind turbine. So it basically tells us the incoming kinetic energy. Okay, that we use the, we can go back to the control volume analysis of the wind turbine. So we basically we told that V1 was the velocity with which the wind approaches the wind turbine, or V1 was the velocity of the wind far upstream from the wind turbine, right? So that is the value of the velocity that is being given here. So that basically means this velocity is the velocity at which the wind approaches the wind turbine. So it is the here that V would be equal to 10 meter per second. And again it is told that the blades are 45 meter long. So we from this we can find the area of the disc, or the wind turbine, windmill disc that we discussed. And yes, so once we know that, it's also told that the wind turbine is at the sea level. So we need to know the density of the air at the sea level, which is usually 1.225. Okay, raw air at sea level is 1.225, and it varies as the amplitude is changed, okay, or increased. So now from that we get that P in will be equal to half m dot v square. Okay, you need to remember this relationship to substitute values. Okay, so from that we get that P in will be equal to half rho av cube. Just substitute the value of rho a can be written as pi r square, and v to get that P in is equal to 3.8 megawatt. Okay. Second part of the question is, how much more power does the incoming wind hit the same wind turbine with if the wind is flowing at 12 meter per second? Now just it is told that the now velocity is changed. So what is the extra power with which the wind is approaching the wind turbine? So to do that, from the in the same equation, just change the value of V to get that P in star, or the value of the power input for 12 meter per second. V equal to 12 meter per second is 6.73 megawatt. Okay, same equation. We are asked to find extra power, so we need to subtract this from this to get extra powers. From that we get that P in star minus P in is equal to 6.73 minus 3.8, that will be equal to 2.93 megawatt. Okay, it was again a very simple question, but you need to remember this equation and then also know what should be the density of the air at the sea level. Okay, and what are the substitutions that you need to make to get the result. Okay, it's very simple question, but again, okay, so again this is a very interesting question again. So it's told that an offshore wind turbine, see, offshore basically tells that the wind turbine is at the sea level. Okay, an offshore wind turbine with 360 meter blades rotates at the speed of 12 rpm. Okay, the wind is whipping along at 18 meter per second. Whipping, or basically tells that it is whipping, basically tells that it is hitting the wind turbine horizontally at a speed of 18 meter per second. What is the tip speed ratio or TSR for the wind turbine, and how does it compare to the optimal tip speed ratio for this wind turbine? Okay, so I guess we have not discussed what is tip speed ratio and the optimal tip speed ratio for a particular wind turbine. So I guess this problem so I chose this problem so that we could discuss these two terminologies which usually used for in respect to wind turbines, so that you can get acquainted to these terminologies as well. Okay. So in this question we have R is equal to 60 meter. This is basically the radius of the wind turbine blades, and N is the number of blades that we have. So N is equal to 3 in this case. Okay, and capital N represents the RPM of the rotation of the wind turbines. Okay, so the tip speed ratio, or TSR, is equal to the tip speed of the blade divided by the wind speed, or the speed with which the wind approaches the wind turbine. Okay, so in this case it was 80 meter per second. So tip speed of the blade basically means that the velocity of the tip of this wind turbine, or the angular velocity of the turbine at small r is equal to r, this capital R. Okay, so there should be, it will basically be equal to omega r. Okay, where r is the radius of the wind turbine, because r will change from various cross section, right, from cross section to cross section. So capital R denotes the radius at the tip of the wind turbine. So we need to find the angular velocity at the tip of the wind turbine. So TSR will be equal to the tip speed of the blade divided by the wind speed. So it will be given by 2 pi n into r divided by 18. So this is basically equal to omega. So once we do the required substitutions, we get that tip speed ratio is equal to 4 pi by 3. Okay. Again, we again saw one another terminology, that is the optimal tip speed for a wind turbine. Okay, so an optimal tip speed for a wind turbine is given by this equation. Okay, lambda, that is this. Okay, lambda is equal to 4 pi with the number of blades of the wind turbine. So in this case, the number of blades is equal to 3, so lambda will be equal to 4 pi by 3, and you can clearly see that this is equal to the tip speed ratio. So the wind turbine is currently moving at an optimal tip speed ratio, right? So that's what we see. Now it's a very trivial question, I feel, but again it it also takes into account the recapitulation capabilities of the students. Okay, so we see here a 50 kilowatt wind turbine operates at a peak efficiency when the wind blows at 26 miles per hour. At this rate, it reaches 62% of the bed's limit. What is the coefficient of power for this wind turbine? Okay, so this question is as simple as it gets. It is telling us that the coefficient of power, or the efficiency at which the wind turbine reaches, is 62% of bed's limit. So the only thing that we need to remember in this question is the bed's limit. What is the value of the bed's limit? So usually, because this type of question usually come in competitive exams, and since we have a lot to remember, students may sometimes understandably forget the value of the bed's limit. Okay, so from today's session, we saw that the CP max, or the bed's limit, was equal to 0.5926. So it is directly told that the maximum efficiency that it reaches is 62% of the base limit. So the CP for this current wind turbine would directly be 62% of the base limit. So it will basically be 0.62 into 0.5926. That would give us, it will basically give us CP is equal to 0.367 or 37%. Okay, it's quite simple. Okay, no tricky part, but the tricky part is to remember the value of the base limit. Okay, so now we reach this final question. So it's again on boundary layer. So we look into it. Okay, a sharp flat plate with L is equal to 50 centimeter and B is equal to 3 meter. B is basically the width of the plate. Okay, so width of the plate. Let me just draw it so that it's not confusing. So this would be the L and this would be B width. Okay. So now a sharp flat plate with L is equal to 50 centimeter and B is equal to 3 meter is parallel to a stream of 2.5 meter per second. So it basically tells us that U infinity is equal to 2.5 meter per second. Find the drag on one side of the plate and the boundary thickness delta at the trailing edge for A, air, and B, water at 20 degrees Celsius and 1 atm. Okay, so this is usually given so that you can know the value of density of air and water at this pressure and temperature. So the assumption that we take is that the flow over the flat plate is laminar. That obviously we need to check by checking the Reynolds number, and there is no flow separation. Okay, and one thing I again forgot to tell, that the boundary layer equations or the boundary theories are only valid up till flow separation. Like beyond flow separation, the boundary layer equations become invalid. Okay, so this is a very important assumption that we take before solving or before describing the boundary layer theory. Okay, so flow separation is disregarded while deriving the boundary layer equations. Okay, this is a very important assumption. Okay, so we do for air first. So for air, we need to find the Reynolds number, because see, all the parameters, the boundary layer thickness, wall shear stress, drag coefficient, everything is dependent on the Reynolds number. So at least for the floor flat plate and boundary and or the boundary analysis for a flat plate, Reynolds number is the first and foremost or most important parameter that we need to determine. Okay, so here for air we see that the Reynolds number is U infinity into L by the kinematic viscosity of air. So that would be equal to 2.5 into 0.5 into 1.5 into 10 to the power minus 5. So divided by 1.5 into 10 to the power minus 5, which will give us a Reynolds number of 3,300, which is well within or much less than the critical Reynolds number of 5 into 10 to the power 5. So the flow is laminar, entirely laminar over flow is laminar over the entire length of the flat plate. Okay, so we can directly use the Blasius relations to get the boundary layer thickness. So from that we get that delta is equal to 0.0087 meter. Okay, and the drag coefficient is equal to 1.328 divided by Reynolds number by the trailing edge. So we get that 1.328 divided by 3,300 is equal to 0.0046. Okay, and the net drag force on one side of the plate would be equal to CD into half rho U infinity square into A, which would give us FD is equal to 0.026 Newton. Okay, only once, since it's told it you need to consider drag force on one side of the plate, so only one area is considered. If it was on both sides of the plate, just multiply this area into 2. Okay, now for water, REL or Reynolds number at trailing edge is equal to 2.5 into 0.5 divided by 1.005 into 10 to the power minus 6, which is the kinematic viscosity of water. Okay, and it is equal to 1.24 into 10 to the power 6, which is now greater than the critical Reynolds number. Okay, so now this is problematic part, that even if the flow is laminar for most of the part of the flat plate, most of the length of the flat plate, but at the trailing edge the flow is turbulent. So it may happen that some portion of the flat plate experiences a turbulent flow. Okay, so now one key thing that I want to say is that the value of kinematic viscosity of air and water. Okay, it's very simple, it's not difficult to remember. Okay, just the order you need to remember. Okay, this value of, or the order of the value of the kinematic viscosity. For water, it is usually of the order of 10 to the power minus 6. Okay, and for most of the calculation it is quite accurate to take the kinematic viscosity of water to be 10 to the power minus 6, 1 into 10 to the power minus 6. And similarly for air, the kinematic viscosity can be efficiently taken as 1 into 10 to the power minus 5. Okay, the multiplicative term is not an important, but the order, this 10 to the minus 5, is very important. So for water is usually 10 to the minus 5, and for for air it is usually 10 to the minus 5, and for water is usually 10 to the minus 6. Okay, so that order, if you remember, it's quite easy to remember these values. Okay, so from there we see that some portion of the flat plate may be turbulent, right? So that's why we get that it's not that large, but it's a bit larger than the critical Reynolds number for a flat plate. Okay, so but again, this is an uncertainty. Okay, like uncertainty in the sense that we since it is very less, like it's not entirely large or very large compared to the critical Reynolds number, and it's very like only very less, it's very like it's not that large compared to the critical Reynolds number, it's very less, only there's a very less difference in the values of this critical Reynolds number and the Reynolds number at the trailing edge. So we can assume that if the plate is smooth enough and the flow is undisturbed, then we can take a very good assumption that the flow will remain laminar throughout the length of the plate. See, this is an assumption. I'm sorry. Okay, just wait for 1 second. Few minutes. See, the concept of critical Reynolds number, or the value of the limiting critical Reynolds number that usually that is being set is usually set for usually a median value, right? Not that coarse surface, not that fine surface, because as I told in the case of flow within pipes, the experimentally or the universally accepted value of the critical Reynolds number is 2300 for the flow within pipes, okay, flow in a circular pipe. But I also mentioned that if the pipe is very smooth and the flow is undisturbed, then the critical Reynolds number, or the flow or the Reynolds number at which the transition starts to take place, can even go up to 10,000, right? So that is what we are imposing here, so that our calculations can become much simpler and we can focus on the physics more rather than some minute mathematical modifications that is required in order to incorporate the turbulent part. Okay, so now if we assume that the plate is smooth and the flow is undisturbed, the incoming flow is undisturbed, then we can assume that this critical Reynolds number can go well beyond 5 into 10 to the power 5. So we can assume that the flow will remain laminar for the entirety of the flat plate. So if we take that assumption, then we can apply the same Blasius solutions for the case of water as well, to find that the boundary thickness is equal to 0.0022 meter in the case of water, which is 1/4 of the boundary thickness of air for the same velocity, and the drag coefficient is 0.0012, which is again 1/4 or approximately 1/4 of the same 1/4 of the drag coefficient of air for the same inlet velocity. But now if we look upon the drag force that acts on the flat plate because of the motion of water over it, so the drag force is now found out to be 5.6 Newton, which is almost 215 times the drag generated because of air. So the key observation here is that even if the drag coefficient is less for water, the net drag force is larger than air. Okay, why? It's efficiently because of the fact that the density of the water is quite high, almost 1000 times the density of air, and this results in a much higher viscous drag force compared to the case of water for the same inlet velocity. Okay, so this is what we need to discuss. So I guess this is all from my side today. So I skipped through some of the concepts from today's discussion. I guess I skipped did not skip, but I moved a bit fast, so certainly there might be some doubts. So for that, I suggest that you can just go back to the video lectures by Professor Gupta. And again, I skipped 2 problems, but again those 2 problems were discussed by Professor Gupta in the video lectures at the end of the boundary layer theory. So you can look upon those problems. They are again quite simple. Again, since we are discussing for boundary layer theory, so the most important parameter that we need to know is the Reynolds number. So we need to calculate the Reynolds number, then just consider the appropriate area to apply to find the drag force, and then the problems are quite easy to solve. Okay, so I guess that's all from my side. So thank you from my side for joining the session. And again, there's again tomorrow one session by some other TA. So I request that you attend that session as well. And if you have any doubt, just put those doubts in the discussion forum. And okay then thank you from my side.